It's like this wavy line. When I take it off, it's completely red or like. Computer modern has never looked so bad. Whatever the fuck.
Yeah, good.
The mic is on, I think.
Yeah,
Sounds like it.
sounds like it. Is anyone using this? Is this for like misbehaving students or?
Yeah, this is the. It's called the
No,
student.
don't worry.
The student appreciation meter stick.
Yeah.
So when we appreciate students. All right, well, people seem ready. You seem ready. Shall we get going? It's quite fun to see you.
Yep, let's start.
For the first and last session of the afternoon, going back to Sebastian.
All right, welcome back. So before we start this lecture properly, let me remind you about what we've done last time. Last time we've set course on this kind of quest to understand the S and B dependence of 2-to-2 scattering in theories mediated by gravitons. And then one thing that we've done is we've focused specifically on this limit here in which the impact parameter is large. Also, S is large, but somehow B is larger than S. Okay, so we're somewhere in here. And then we studied the single graviton exchange at tree level. Okay, so what we found is that I told you about this impact parameter transform. I've kind of recalled the definition on here in these two first lines. So we had S as a function of S and B was equal to 1, which was the disconnected term, plus some kind of a Fourier transform of the ST-dependent amplitude, which we computed using Feynman diagrams. There was this exponential here, which is basically a Fourier transform between the impact parameter and the momentum transfer. And last time I've actually decided to rewrite it a little bit today. Last time I wrote it as a d-2 dimensional integral. Following some questions yesterday, I actually decided to rewrite it a little bit as a d-dimensional integral, but with 2 delta functions. So these 2 delta functions make it obvious that if I look at the momentum of the first or the second particle, and I dot it with the momentum transfer, q, which is the momentum going across in this direction, then they're orthogonal to each other. So I set them to 0 using these 2 delta functions. You can work out of the Jacobians. They work out to give you the formula that we've seen last time. In any case, what we've done yesterday was to actually plug in the value of the tree level exchange. And then what we've seen is that this gives you this purely imaginary answer that had some numerical factors, but crucially is proportional to G because it's the first order in perturbation theory, S because of the spin dependence of the amplitude, and then B to some power, which you can essentially fix by mass dimensions. Okay, so just to, I'm going to use this notation a little bit in order to cut down on writing the same object over and over again. And also this is the notation that you would find in the literature. People often call it 2I delta of 0, and we're going to understand why it's called delta of 0 in this lecture. In any case, one of the puzzles that I left you with at the end of the last lecture is studying unitarity of this amplitude. And then we've seen that essentially because the amplitude grows too fast at large S, then at some point this value, this number here is going to exceed 1, which violates unitarity. Okay, and then we know that on this graph here, the place where this happens is going to be this is actually why I decided to rewrite it on a log-log basis. So the place where this function here becomes of order 1 is actually a straight line that you can plot somewhere in here, okay? So what we've understood is that if you go across this line, then you start violating unitarity. This is actually, to those of you who don't have a significant particle physics background, let me just mention that this is the usual way that we try to understand that there could be new physics around the corner. Okay, you compute something to lowest order, say it's tree level, and then you discover that the amplitude grows too fast, so that means that there has to be something new that rescues the amplitude and unitarizes it such that it becomes below the unitarity bound. And this is, in the past, how people have put bounds on the masses of the Higgs boson, of the W bosons, and things like that. So that's how it's quite a common approach. Okay, so the puzzle that I left you with is that there has to be something that completes this amplitude that rescues unitarity. Okay, so maybe I already heard that many of you resolved that puzzle, but maybe you can, someone can speak up and tell me what's going on. Yeah, exactly. So maybe as foreshadowed by the ellipsis in here, you need higher orders in perturbation theory. So what this means is that you need to include more vertices in here, which carry the square root of g in perturbation theory. And that automatically means that, well, it's impossible to add more vertices without adding loops. So this forces you to talk about, if you wanted to go across this barrier, to talk about loop diagrams. That's actually, it's supposed to be a little bit puzzling, especially if you have not seen this before, because we learned in QFT courses that loops are suppressed by h bar raised to the loop number. Okay? So what's the resolution of that? Since here we want to talk about the classical physics, that doesn't seem entirely right? So exactly. Exactly. So let me kind of rephrase what you said, also to have it on the record, that the usual power counting with h bar assumes that all the scattering energies and angles are kind of order 1. But now what we're actually doing here is taking some very extreme limits. And more specifically, the ratio of -t over s is very, very small. You can actually predict how small it is. It's supposed to be of order h bar squared. And this means that the usual power counting changes. And now loops can also include classical corrections. Okay? So this is what we're going to start exploring today. And tomorrow we're going to include corrections. So I'm going to start with, I guess the name of the section is the iconal approximation. So the way that you should think about the iconal approximation as the relativistic version of the WKB approximation, which hopefully all of you have seen in a lot of details in your quantum mechanics courses. Okay, so this is essentially what we're going to study. So let me start with the claim. I'm going to claim that there's going to be the following object, S of S and B. I'm going to add subscripts iconal. And then I'm going to claim that it's going to consist of the following series of diagrams. So first of all, we have the disconnected term and the tree-level exchange. So this term and this term. So that we've seen. But then on top of that, we're going to do what you've suggested, is to add higher orders in perturbation theory. But actually, what I'm going to do is only add specific diagrams in which we have the two word lines as before, and then the gravitons will attach to them pairwise. Okay, so for example, at one loop, You can do it in this way or this way. So this is called the box diagram, and this is called the cross box diagram. Okay, so then there's going to be a claim that I can keep doing this. Okay, and at some high loop order, I have to include all these kind of diagrams. Okay. And the claim is going to be that studying this series achieves two things. First of all, it's going to unitarize the amplitude. But second of all, and perhaps more importantly, it can also be computed. Okay, so when I was a graduate student and I first have seen this claim, I couldn't believe it, because in my QFT courses I've spent hours and hours and days and weeks trying to compute one loop amplitudes. Probably most of you have never computed 2 or 3 loop amplitudes. It becomes insane. But this claim nevertheless tells me I can actually compute not only 1, 2, 3 loop, I can compute an arbitrary number of loops. Okay, so that sounds like an insane statement. I think actually it's one of the greatest achievements of quantum field theory that you can actually make this computation. Okay, so how many of you have seen this exponentiation or the unitarization in action before? So basically, almost no one. What I wanted to do today is in the first half an hour to give you some kind of flavor of the magic that goes into this kind of computation, why it simplifies, and how do we see it actually exponentiates. And then in the second half of the lecture, we're going to extract some physical consequences of this exponentiation.
Can you clarify what you mean by can be computed? Because in principle,
Yeah.
higher loops could just keep using some form of generalized uniformity, right?
Is this a good clarification? Okay. Okay, so let's start. Oh, yes.
Did you say that we're only going to include some diagrams?
Yes, so we're going to include the diagrams of this type. They're called cross ladders. The specific thing about them is that the gravitons, basically a graviton is attached to the lower word line and to the upper word line in all possible permutations. So at one loop, there's these two options. There is going to be a factorial number of options otherwise. But we're not going to include like graviton self interactions at first. And we're going to come back to them actually tomorrow. Okay, so as I mentioned, there's going to be two topologies that we're going to do at one loop, which is the first order that we've not done so far. There's going to be the box diagram. And there's going to be the crossed box diagram. Okay, so let me start by maybe doing a big picture with the conventions. Okay, so the incoming momenta are going to be P1 and P2. And then the outgoing ones are going to be P2 prime and P1 prime. Okay, and then we're doing a loop computation. So we need to attach some loop momentum. So there's going to be a loop momentum L1 and L2 in here. Okay, so by momentum conservation, this momentum here, we can solve it either by this vertex or this vertex is going to be P2 prime minus L2. And this one, I'm going to write it as P1 minus L1. Okay? So let me keep this up so that we have this for reference. Okay, so the box, the Feynman diagram of the box is going to be written as follows. So first of all, we have to integrate over the two loop momenta. Okay, there's some factors of the 2 pi and so on, so don't worry about them. And then on top of that, well, I wrote it in a bit funny way because I've introduced two loop momenta, so there's a constraint, of course. So the constraint is going to be the delta function that is going to be P2 minus P2 prime plus L1 plus L2. Okay, so just the momentum conservation. And actually, this combination of P2 minus P2 prime is basically the transfer momentum, except I think in my notation it's minus the transfer momentum, like this. Okay. Okay, so this is just the measure part, and then on top of that, we also have the propagators and the vertex factors. Okay, so for the propagators, we have the two massless propagators, L1 squared plus I epsilon. So it was probably evident from the previous lectures, but I'm using mostly minus conventions. L2 squared plus I epsilon. You might think that I'm being a little bit, with all these I epsilons, but they're actually going to play a crucial role. So this is why I wanted to include them. Okay, and then on top of that, there's going to be the two massive propagators. So let's reinstate the masses on the external particles. One is going to be P1 minus L1 minus m squared plus I epsilon. And the other one is going to be P2 prime minus L2, same. Okay, and then on top of that, we're going to have some numerator, which comes from contracting the vertices. For now, I'm just not going to worry about it because it's going to simplify in a second. Okay, so hopefully that's not controversial. I've just written a Feynman diagram. Okay, but now is the time for the simplifications. So for simplifications, let me just take this factor in here, these two inverse propagators, and let me call it C box, 1 over C box. Okay, so that I can just copy it to a next Blackboard. And now what I'm going to do is I'm going to make carry out some simplifications on this diagram. Okay, the first one is going to be that, you see, the reason why I've introduced two loop momenta L1 and L2 is that I wanted to be as symmetric as possible. But there's still some little choice that I call this one L2. So the first thing that I'm going to do is just symmetrize over the two choices. And the next thing that I'm going to do is expand in the limit as these gravitons being exchanged are soft. Okay, so soft meaning that I'm going to use the fact that the L1 and L2 are much small, the absolute value of that is much smaller than P. That's the question.
So in this, are we assuming that we have a quantum theory of gravity?
Yeah, that's an excellent question. So I was just going to get to that point. Well, we could have kind of started here. When I said that we're going to include loops with gravitons, you might be very much worried that there's going to be problems with UV divergences, renormalization, and so on. These are valid concerns. However, what we're going to do is we're going to study the limit in which the gravitons in both cases are soft. Okay, so the momenta are very small, small compared to P's. And this is the region which is the exact opposite of the region in which usually you have UV problems, which is the L's being large. So this is a sign of the problem that in this regime, we actually have complete control over this computation. We're going to be only sensitive to this soft graviton exchange. And all the problems with non-renormalizability and all that, they just go away. Yes, sorry, the question was?
Why can you expand in small L1? Because I thought you're integrating over that.
Yeah, so the question is, why can we expand in the L1? Because we integrate over the loop momenta. So this is actually similar to the question that we had last time, which is I introduced the, we had the diagram that I being exchanged at tree level is being solved. And then the answer there was that I could in principle include other contributions, but they're just going to be subleading. In this case, they included contact terms in the B expansion, in the B Fourier transform. So the same thing, I'm not going to go through the careful analysis here, but perhaps you can trust me that if you do this similar analysis and try to understand the other regions in which L is hard, not soft, they are actually subleading in the large, in the high energy limit. Yes.
I might have missed it, but what is this case for only looking at these type of diagrams, not like similar corrections?
Yeah, that's a great question. So the question was, why are we looking at these classes of diagrams? So the answer is, if you did a more careful power counting, which we're actually going to come back to tomorrow, you would see that these are the leading diagrams that contribute. So for now, I just wanted to present like how they resum. And next time, we're going to see how including corrections is actually giving a consistent correction to the resummation. OK, so what we're going to do is, as I said, symmetrize and expand in the limit when the loop momenta Li are much, much smaller than all the external momenta. Since because of the delta function, the loop momenta being very small is also compatible with the momentum transfer being small, which is what we want. And so this is the limit of soft gravitons. Let me kind of write it down. The thing that I mentioned is that in this limit, there's no UV problems. In other words, the gravity is entirely predictable, computable in the high energy, in this classical limit, and we don't have to worry about all the non-renormalizability and things like that. Yes?
Just to confirm, in tree-level calculation, this divergence from the gamma is IR, right? And the equals 4, for example.
The question was about this divergence here, whether that's an IR divergence. Yes, it's an IR divergence in 4 dimensions. Oh yeah, sorry. So this formula I wrote it more carefully last time. This is in D dimensions. When D approaches 4, this becomes a log, and you need to regulate it. Yep, excellent. OK, so let me come back to this factor of C box. The only thing that I'm going to do is I'm going to just copy it and then symmetrize it. So I have P1 minus L1 m squared, and then P2 prime minus O2.
Does that mean that the numerator is bisymmetric?
Yes, it is. Yes. OK, so we're going to have this term and plus L1 and L2 exchanged. Yeah. OK, and now I can actually make some simplifications. I can expand this product here, this square. So this square gives me P1 squared, but P1 squared is the mass squared of the particle because it's on shell. OK, minus the cross term twice P1 dot L1 and plus L1 squared. OK, and likewise here, this is m squared minus twice P2 dot L plus L2 squared. OK, and now I can actually use some simplifications. So the first simplification is that the m squared term cancels out here and here, and likewise here and here. And the second simplification is going to be that I can cross out, because of this limit here, the L squared is much smaller than P dot L. So I'm going to cross out these ones too. And you see that what happens, previously the inverse propagator here was quadratic in L, and now it becomes linear. Okay, so we say that the propagator iconalizes. Or we call it the iconal propagator. Okay, so I'm running out of space, so let me carry on in this blackboard. Okay, so in the second step, let me just copy the first step. This, then this. Okay, one additional simplification that I'm going to make is that here, P2 prime is up to small corrections the same as P2, right? Because the difference between P2 prime and P is just the momentum transfer, which is Q, and that was subleading. So that means that in this equation, I can actually replace P2 prime dot L with P2 dot L2. Okay? And now, in the symmetrized term, well, I can do the same. So I exchange L1 and L2, so this becomes L2. This becomes L1. And now I can use the following trick. So I'm going to say that this one is minus P1 dot L1 plus Q dot P1. Maybe I should write P1 dot Q. Okay, so once again, I've used the momentum conservation delta function that I can write L2 as minus L1 plus Q. Okay, and once again, this term here is subleading, so I can cross it out. It's subleading because we're working in the kinematics in which P dot Q and P dot Q are 0. Okay. And then I think the final change that I wanted to make is also do the same thing on this term here. So this term is going to be minus P2 dot L2 plus something that is subleading. Okay. Okay, so I've made some simplifications. Maybe at first it doesn't look like things simplified a lot. And in fact, if you just consider this diagram, they've not simplified a lot. But what we're going to do next is we're going to come back to our crossbox diagram and see that there's going to be a lot of cancellations. Okay, so the crossbox is going to look like this.
Are your two terms just the same now?
Oh, did I make a mistake?
I'm not saying you made a mistake.
No, they're not the same. So this term, maybe I was not careful with how I put my parentheses. This one is a plus, this one is a minus, this one is a minus, and this one is a plus. I can rewrite it if that's helpful. So let me maybe highlight it just to, yeah. The minus sign here. And then in this case, we have a plus sign coming from those two things and a plus sign coming from those two things. Okay, so they're not the same terms, but they're almost the same. Okay, so then now let me come back to the cross-box diagram. Okay, so once again, P1, P2, P1 prime. And then let me call this, it doesn't matter, but let me call this momentum L1 and this one L2. Question? Yes, so the question was if I dropped the term P dot Q, and the answer is yes. So in all of those computations, I'm assuming that P and Q are orthogonal to each other, which is eventually going to be imposed by these delta functions. Okay, so now I have to be careful about which blackbirds I erase. I guess let me do this one. Okay, so let's analyze the crossbox diagram. So first, let me point out some commonalities. Okay, so we're going to have essentially the same formula as here, same L1, L2, delta function. There's going to be, operator stays the same, this stays the same. The only modification is going to be in these two terms. Okay, and let me call that term C box, sorry, C crossbox, I guess. Okay, and then we can write what it's supposed to be. So I should have put this on. Hopefully I'll solve momentum conservation, but I made these choices just to be consistent with my notes. L2 plus P2. So then what I do is I just look at the propagators, I copy them. I have this term, and then I have this term. Once again, I symmetrize in L1 and L2. Okay. And then I applied the same tricks. Okay, so the first trick was to iconalize the propagator. So it linearizes. So I get 1/2. And then in this case, I get minus twice P1 dot L1 plus I epsilon. And then in this case, I get plus twice P2 dot L2 plus I epsilon. Okay, and then plus the symmetric term. In the symmetric term, let me make the changes kind of straight away. So this is supposed to be P2 dot P1 dot L2 plus I epsilon. But then I can use the same trick as over there and write L2 as minus L1 plus dot dot dot. So let me just do that straight away. And if I can fit it in here, I get minus P2 dot L2. Okay. Okay, any questions? All right, so now I can compare this term and that term. So you notice that all of them are of the form where I have the invariant P1 dot L1 and P2 dot L2, plus I epsilon, and so on and so on. The only differences are in these plus minus signs. Plus, minus, plus, minus. Okay, so to make it slightly more obvious, let me write the sum C box plus C cross box. Okay, and let me write it in this way. Yeah. Sorry. Okay, so it starts looking exciting. So let's first maybe verify that this is the correct expression. Yes.
Touching on earlier, why are we allowed to symmetrize?
sorry, symmetrizing is only because we symmetrized in the labeling of L1 and L2. That's our. So I'm just doing that to make the answer as symmetric as possible. Any other question? Yeah.
Doesn't the integral take care of that already?
Yeah, it does. It does. So the question is, doesn't the integral, like the integrated answer is of course independent of the choice, just like to see some cancellations at the level of the integrand, I'm doing the symmetrization before. There's a question at the back.
What's the story about the numerators?
Yes, I forgot about the numerators. Let me actually come back to that in 3 minutes. Yeah. Okay, so maybe let's verify first that this expression that I wrote is indeed the sum of the two terms. So one thing that I can do, let me use colors. One thing that I can do is look at the first and last term, I believe. Let me first look at the first and first term. This one and this one. Yeah, this one and this one is this term here. Okay, another term that I can look at is the second one and second one. And that term is this term. Okay, so that takes care of the boxes. And now another thing I have here is the opposite, the first and the last term. Hopefully, if I've not made a mistake, should be the second term in here. And then, as you can predict, the last term is going to be this one. So this one and this one. Okay? So is that cool? Well, it's cool because I can use everyone's favorite identity, 1 over x plus I epsilon minus 1 over x minus I epsilon. It gives me, it's at least my favorite identity, is giving me a delta function. So let me write it down first and then come back to your question about the numerators. Okay, so I'm continuing this equation in here, and that equation is going to give me, if you remember, minus 2 pi I squared, because we have 2 of those identities, and I have delta function of twice P1 dot L1 from here, and a delta function of twice P2 dot L2 from here, right? So that's the amazing thing about the summing over these two diagrams, at least in this limit. Naively, it seems like I have to do a lot of integrations, but actually what popped up are these delta functions. So they actually simplify my integration quite a lot. And it's also a lesson in the fact that you should keep track of your I epsilons. If you forgot about them, you would just get a 0. Okay. Let me also mention one coming back to the numerator story. What we discovered here is essentially that all the propagators have to be on shell. And the reason, so basically, it means that these propagators, this one and this one, and this one and this one are on shell. So that means that if you're computing contraction of the vertices, you have the contraction of this vertex and this vertex, which essentially lecture, and that was the factor that gave us the numerator. So now, because of this cancellation, is essentially just a square of that. So let me write it down. This is minus 8 pi g, and then there was this factor of gamma s that we've seen last time, all squared. Yes?
So, just a question on the order of the logic. To add up C bar, since
Yeah.
response, don't we need to assume the numerators are the same?
Yes, yes. So the question was whether this was the outcome or whether this was an assumption or the outcome. So there's a more responsible computation that would take us like 15 minutes to discuss the exact vertices, how they contract, and so on. But the outcome of the discussion is that they just square. Okay, so I kind of shuffled that under the rug a little bit. Okay, so now what we can do? Yes, exactly. So the question was, yes, yes. So the same computation would happen in gauge theory. The only change is that you would have a numerator, which is the numerator from with a different S dependence. Okay, so this iconal exponentiation is a generic feature of many theories. And now what we can do in the last step is let me just combine everything that we've learned so far. Okay, so combine both diagrams. Okay, so this gives me at least the asymptotic contribution to the one loop scattering amplitude. Okay, let me pull out these factors of 2, and then the kinematic factors -8 pi g gamma s squared. There was a minus sign. Okay, and then I have these integrations over the loop momenta. Let me copy that. Let me actually do it this way. Okay, so you see that the answer almost factorizes. It almost factorizes. The only thing that I have not included yet is this delta function, which we should not forget about. Okay, so this is all times delta function of, I guess I called it minus q plus L1 that L2 plus L2. Okay, so you see, this answer is almost exciting. It would be exciting if we didn't have this delta function, because then it would be just a square of the tree-level computation. So let me emphasize the fact that this actually does not factor. But on the other hand, this gamma function here, delta function here, is also the only Q dependence. Sorry, I'm cramming a little bit. Okay. And it turns out that this is basically as far as you can go if you're doing things in the ST variables. Basically, you have to carry out the remaining integrations and do the computation. That's it. The additional simplification doesn't come until you actually do the impact parameter transform, in which case there would be an actual factorization. So this is what I wanted to explain next. Okay. Okay, so basically what I have to do is I have to take this answer here and plug it into the transform. But I just mentioned that the only Q dependence, this is a Q Fourier transform, the only Q dependence is this. So it actually looks fairly reasonable. So I can come back to the impact parameter transform. Okay, and the transform looks like this. So I have the q-dimensional integration, and then let me drop all the constants. The identity that we're going to need is this, then the exponential, and then I can just copy the one-loop answer, but actually the only relevant term is this one, right? So you see, this is where the magic comes from, because now I can use this d-dimensional delta function on the integration to localize q. So basically, I solve this one. And the answer are actually factors. Into e to the I b dot L1, e to the I b dot L2, and then a delta function with 2pi p1 dot q, which is now L1 plus L2. And the other one, and actually there's one extra small exercise by computing some Jacobians in here. You can show that these delta functions can be actually written as delta of twice p1 dot L1 times delta of twice p2 dot L2. Okay, so that's the result we're hoping for. Everything here cleanly factors into the L1 and L2. So I can stick them in these formulas in here and compute. And this is what gives me the one-loop factorization. Excuse me? Square of delta function.
You have the delta function right off the top four, and then you already had the same delta function.
Let me think. Yeah, I think so. Yeah. Let me see. Yeah, exactly. So let me copy that. So there's we're going to have factorization. The value of the one loop as a function of S and B is going to be 1/2. The 1/2 was this just a half coming from here. And then the rest squares.
So this one plus this.
Excuse me? What's the question?
This is just the one loop contribution.
Oh yeah, sorry. This is the dot 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 at one loop term. Okay, so there's going to be this term, and then there's going to be this term with L2. Okay, so inside of them they have these gamma functions and so on.
Isn't the, didn't you just impose p1 dot L1 equals 0 those delta functions and get delta of p1 dot L2?
What did you want to do?
From the other delta functions, you have p1 dot L1 equals 0.
Yeah.
So you can have delta of 2 times p1 dot L2. And delta of
I think, sorry, that's the typo that I did. Exactly, sorry, I got very confused here. So yeah, I use them for this purpose. So then I can distribute in the first term here. I can use this delta function and this delta function. Yeah, thank you so much. And then after I do that, the result here and the result here is the impact parameter transform of the tree-level result. Okay, so this is S3 as a function of SB, and S3 as a function of SB. Okay, so to summarize, we've combined both Feynman diagrams. In the ST space, there was almost a factorization, but not quite. The additional ingredient that we needed is this impact parameter transform, after which we found that literally the one loop amplitude is 1/2 times the tree level squared. Okay, so to complete the story, I guess I can erase those. You can extend the story to higher loops. I'm not going to torture you with that. Hopefully you can believe that the same mechanism is going to guarantee that summing over now 6 two-loop diagrams is going to, by this cancellation mechanism, is going to give me a cube of the amplitude. And then at the L loop order, I'm going to get the elf power. And that result is known as the iconal exponentiation, which in the context of gauge theories and non-relativistic theories has been known for a while, but in the gravity context, it's been described by Kabat and Ortiz around 92. And it tells me that after summing over all of these diagrams, so doing the sum over crossed boxes that we had at some point, I'm going to get the following formula. 1 over L factorial, and then S3 to the elf power. Okay, which of course exponentiates. And then using the notation here, I can notice that the tree-level exchange itself was purely imaginary. So it actually exponentiates into a phase. Okay, let me use that notation here. And yes?
One loop case had a 1/2 up front here.
Yes.
Right, so it's like 1/2 as
Oh, did I?
the 1 over L factorial. That's the one.
Oh, sorry, yeah. So the one loop was, so I have to have this. No, it's fine. Just L is not the number of loops, it's just the L to the. Yeah, okay. Okay, any other questions? So I should point out that this conversion of the amplitude having 1 plus I times S thing, now it became in the exponential. This is, of course, the unitarization that we are after. And it's unitarization because how large S is, it just changes the phase, but the absolute value of this object is always 1. Let me leave you with a couple of exercises here. I know for a fact that at least one person in the audience is actually solving this. So the first exercise is to restore the factors of h bar. And show that S3 goes as 1 over h bar. So what this means is that if I restore the factors of h bar, included them here, I would get this. Of course, what do we need from our WKB approximation, right? In the iterating phase. So this is roughly like what you're familiar with from the localizing the action and so on. But it might be actually a little bit confusing. It definitely goes. It's at odds with the power counting that we usually do in the QFT courses. So what this actually means is that at tree level, I have 1 over h bar. It's one loop. I have 1 over h bar squared, 1 over h bar cube, and so on. So instead of the contribution more and more suppressed in the h bar, they actually become more and more enhanced. But you see, this is needed if you wanted to build up the phase. Okay, so these terms that grow and grow more and more with the factor of h bar is something that we called superclassical terms. Okay, I'm going to come back to that in the tomorrow. Yes. Yes?
So you're going to tell me about was that this should be bounded by 1.
Yep.
Terms that we threw out. We know that the subroutine.
Yes. I was going to pose that as a puzzle at the very end. So let me not repeat your question at first. Before that, let me leave you with another exercise. Is to show that you see, it's funny that on the one hand, I have the power law here. So if S value at higher and higher loops, it gets its power law enhanced. But on the other hand, there's 1 over L factorial suppression. So it has to be that there's some term in the middle that dominates. Okay, so the question, the exercise, is to show that the most dominant term is actually at the loop order which roughly equals to the value of the tree level amplitude. It's actually quite fun. You can plot it, in your favorite software, and then see as a function of loop order which term here dominates. I recommend to plot that on a log scale so that you can see there's a very sharp peak around this loop order.
Is that L the L in your original sum, or is that L the number of loops?
It essentially doesn't matter because L is large anyway, so it doesn't matter. Let me put a tilde here. Okay, so let me speed through the remaining topics that I wanted to discuss. The first thing is that we've seen that it was kind of difficult to compute things in momentum space, but it was quite easy in the impact parameter space because the thing exponentiated. But now the thing that you can do is you can first exponentiate it and then Fourier transform back into the momentum space and then read off the result. So back to the momentum space. Essentially what you do is you do an inverse Fourier transform. Let me actually do it in 4 dimensions since I'm kind of running out of time. The object that we can compute is the iconalized momentum space amplitude, which is essentially, the inverse transform.
Just so you know, Sebastian, you have another 17 minutes.
I think I'm still running out of time, but yeah.
I was just afraid you thought you were done at 30.
Yeah, no, not quite. Oh, but I thought we have until 5. No? No, don't worry. Okay, so the thing that we're going to do here is we're going to come back to momentum space. Let me use this fancy notation in here. And I believe if I actually wanted to do the Fourier transform, I have to pull out the 1. the inverse transform. Okay, so I get this.
That board is going on its track.
Okay, that's okay. So let me just give you the final answer. It's an integral that you can compute. It's not horrible. And the answer to this integral is that I get minus I 8 pi g s squared over t. So this is the result that we've seen. Well, it's the tree-level exchange. But now that's multiplied, and it's multiplied by a pure phase. It looks like this. As you might expect, the answer is actually infrared divergent. So I've included the IR regulator in here. Raised to the power of minus I alpha g, where alpha g is just gs divided by h bar. Okay, so you see that back in the momentum space, the only effect of iconalization is that I have the original propagator in here that dressed with some phase in here. Okay, so this is a pure phase. That's actually a beginning of a wonderful story in which you can think of this whole mode here as a new mode. It's usually called the graviregion, which is the collective behavior, summarizes the collective behavior of all these gravitons being exchanged in the T channel. Okay, as I mentioned before, there's also a gauge theory analog of the same story. So, for example, you could have done the same story in QED, and this is how you would find there's some interpretation of the bound states that are here. So, for example, if you can study the bound state of the hydrogen atom or the positronium by looking at the positions of these poles here that have the interpretations of the bound states. In the gravitational context, however, these are usually understood as spurious poles. So they do not have a clear interpretation. And the reason for that is that if you actually study where these poles come from, back in the Fourier transform, they actually come from the region of low B, which is the one in which the approximation was actually not valid. And if you modify the low B behavior, these poles actually get smeared out. And that's why I call them spurious. Yes?
Can I ask a question about the location of the poles in QCD?
Yes?
Here, I see that the poles would appear along the imaginary axis in S, whereas I would imagine bound states would be in the real axis.
So the question was the poles appearing in the S channel or in the T channel. In this case,
Like the poles in S, right? Because it said 1 minus GS over H times I
Yeah.
0.
Yeah.
So they would be on the imaginary
Yeah.
axis. So why do they have the interpretation of bound states?
It has to do with the Reggie theory, in which we can understand the exchange in the T channel as the S channel poles and so on. So I didn't want to get into that. But at least if you look at the spectrum, for example, in the case of if you had a very light particle and a very heavy particle exchanging photons, you can read off the spectrum of the hydrogen atom by just looking at the positions of the poles of these gamma functions. Okay, so as the final topic today, unless there's any questions. Yep.
Would there be poles in non-electricities now in the upper half of S?
The question is about whether the poles would be in the upper half S plane. And let's have a look at that. Well, the answer is no. Well, sorry, actually.
1 by gamma is entire usually, so poles only come from numerator.
Oh, I see. Okay, never mind. I got you. Yeah.
Okay, good result. Well, one thing that you have to be careful about is that some of these poles could be on the second sheet. So I believe the reference that I've included on the Google Drive by Kabat and Ortiz actually is trying to interpret these poles, although I would not trust that part of the paper 100%. Okay, so as the final thing that we're going to discuss today is the saddle point analysis. So what we're going to look at is we're going to look at this inverse transform in here and trying to interpret it using saddle point methods. Okay, so this is justified by the factor that inverse 8 bar. Okay, and what this is going to tell us about is we're going to think of this as, well, we're going to apply saddle point approximation here, and from that we can study the asymptotics of the ST-dependent amplitude. Okay, so the first step in doing that is looking at for the stationary phase. Yeah. Oh, yeah, the question is why are we doing the saddle point? And the reason why we're going to do the saddle point is to understand which B dominates. And this will also tell us which Q dominates. So we're going to be able to read off the classical angle. Yeah, we wanted to keep dependence on the B in here. Yeah. Okay, so the stationary phase basically means that we look at the exponent, and then we compute the derivative with respect to B. Okay, so there's two parts. I can ignore the 1, because 1 just gives me a contact term. So then I look at the exponent, which is B dot Q. And then the rest, which is in my notation twice the real part of the delta. And I look at the real part because there's an I up front. Okay, so this actually gives me right, so let me just develop this equation, right? So it gives me Q is equal to twice the derivative of delta 0 as B. So delta 0 is already purely real, so I can drop the real parts from the formula. Okay, so then you can actually compute this. And what it tells you, well, let me give you the full formula. What it tells you is that the integral we're looking at is localized at this specific value of Q. Okay. So because we are computing a B derivative, one thing that changed is this power of B here. And also because of the D minus 4, it's going to cancel some of the divergence in the gamma function. Okay, so if you simplify the expression, it looks like this. So one aspect of it is that it's actually IR finite in D equals 4. And this quantity here is usually called the impulse. Okay, so this quantity tells us what is the kick the effective kick that my exchange of the gravitons gave between the two word lines. Okay, and actually one of the maybe follow up to the little exercise that I described over there is that what you actually can do is you can compute the expected value. Maybe I can call it like this: the expected value of the loop momentum that is being exchanged. The expected value of the loop momentum basically looks like this Q. Maybe let me call it Q star. divided by the number of gravitons that are being exchanged. So if you trust the exercise, the number of gravitons is proportional to the tree-level answer. Yeah? Which power of b? Where? Here? d minus 4?
Why is that d minus 2 or something?
You would like d minus 2. I'm just plugging in this expression here.
Take the derivative, right?
Yeah. And there's a b in the numerator. I just included that b in the numerator because it's a vector. So.
But don't you just take the derivative raised by 1 power, but then also you have to normalize the chain rule, so it's. Well, also.
Oh, sorry, did I write it upside down? Oh, sorry, did I? Yeah, I think I just made a typo in my notes. Thank you. So the point is that the absolute value goes like 1 over b to d minus 3. Yeah, thank you. Okay, and then one thing that I was mentioning here is that this is the kick, the total kick that you give to between the two word lines. Now we can actually estimate what is the kick of the individual graviton. Okay, so after you install the factors of h bar, so this was actually very good that you pointed out the typo in here. I take the difference between this q and the delta 0, and the difference is 1 over b, right? And if I reinstall the h bar, then it means that it's actually quantum suppressed, and it's also suppressed by the 1 over b. So what is the story? Well, the story is that I'm exchanging an infinite number of gravitons. Each of them gives me an infinitesimal kick. So I can think of my word line as being bent slightly more and more, such that in the end, what I get is some finite bending. So let's actually estimate this finite bending. That finite bending is essentially the scattering angle. Okay, so the deflection angle. Okay, the deflection angle, recall from the previous lecture, was given by this formula. Divided by s in the master's case. So if the angle is very small, I can expand this cos, and I can match the theta squared to t over s with a factor of 1/2. Okay, so if the angle is small, I can actually approximate this as minus square root of 4t over s. Okay, that's just the Taylor expansion. And now what I can do is, realizing that t is minus q squared, I can actually plug in this formula back here. Okay, so let me skip the exact coefficients, which you can just match in here. And what I get is what I get is 1 power of g upstairs. It would be a power of s, but it's compensated by a square root of s. So that gives me a square root of s. And then the rest can be restored by the mass dimension. So it looks like this. Okay, so this is essentially, let me in pictures, let me repeat the story. We studied the two particles. They exchanged gravitons, and this infinitesimally bent the trajectories. And then they started exchanging more and more gravitons. I'm exaggerating a little bit here. And essentially, in the end, there's some scattering angle in here, which, well, in the picture is exaggerated, but in practice is actually infinite as well. Okay? And of course, this scattering angle, you can come back to your books on GR and confirm that this is the well, at least in the master's case, which is the one that we studied here, this is the correct bending of trajectories. Yes?
What does this Li expectation value mean in the picture?
The expectation value of Li is there's going to be some momentum that is being exchanged through a single graviton, just the loop momentum in our previous language. It just means that it's infinitesimal. It's of this order. But then in the end, we exchange an infinite number of them. So we get infinite number times this, such that observables, such as the deflection angle, become finite. Okay, so let me finish with, in my last minute, with the another famous prediction that you can derive from using the same technology, which is the Shapiro time delay. So Shapiro time delay, in the same way as Q and B are Fourier conjugates, in the same way, the time delay is conjugate to the energy. Okay, so if you wanted to compute the time delay, you can do it by computing the derivative of the real part of the action of the phase shift divided by the energy, which in our language is square root of s. You can actually compute it. If you get all your powers right, it becomes g square root of s with a different exponent. Okay, and that turns out to match the Shapiro time delay in GR, which is another famous prediction of general relativity. One aspect of well, I've not told you what the hashtag is, but the hashtags in my notation are always positive. And this is positive, positive, positive. So in GR, the time delay is always positive, which is a known result. Just to make a little connection with the previous lectures 2 weeks ago and this week, in principle, what you can do is you can also add corrections to GR, like higher derivative corrections, Gauss-Bonnet in higher dimensions, or R cube. And those corrections, while you can go through the whole technology, you can include them and so on, that would actually give you a negative contribution to this time delay. So one way that we would put constraints on the higher derivative corrections, or the Wilson coefficients of those higher derivative corrections, would be by imposing that the time delay is positive. In other words, that there's no causality problems in your theory. And this would give you actually bounds on the Wilson coefficients in modifications of gravity. So I've actually included a famous reference on that in on the Google Drive. Okay, so with that, I think I'm on time. So let's wrap it up for today and see you tomorrow.
All right, well, just to remind everyone, no fourth lecture today, no 9 a.m. lecture tomorrow. So we'll see you at 10:45. There will be coffee before that if you want to come a little earlier to have coffee. And reminder, tomorrow night, 6 p.m. is our banquet. Bring your ID and bring